So between the means. So it appears that the users do have a lower GPA than the non-users. Okay, other thing I should have pointed out in this before I went on was that notice that with the sample sizes, the sample size were 85 and 128. Okay, so just you can make a note of that N1 and N2 were both greater than or equal to 30. Okay, that was one of the two conditions, and I should have said that before in this. The N1 and N2 are large enough. Okay, by the central limit theorem, it allows us to do this and be pretty happy with our results. Okay, move along to the next example here. Okay, now we're going to look at a hypothesis test. Okay, so that same example, we're going to test the claim with alpha equals 0.05, and the GPA of students who use the site is less than the GPA of students who do not use the site. So now we're looking at the GPA of students who use the site less than GPA of students who do not use the site. Okay, so now what we're looking at is we're trying to make a comparison between the GPAs. Okay, so testing a claim, that needs to tip you off that it's a hypothesis test, which means we need to write our hypotheses. Okay, so we have our null hypotheses and alternative. Well, the GPA of students who use the site less than the GPA who do not use the site, that would be that mu1 is less than mu2. And the null, mu1 equals mu2. And again, we're looking at the first group as being the users and mu2 being the average GPA of the population mean of the non-users. Okay, and that is the claim that mu1, the users, have a lower GPA than the non-users. Now, based on our hypothesis, based on our confidence interval that we just did, it appears that this is going to work out to be support the claim that mu1 is less than mu2. But we have to pay attention to the alpha value, remember. Okay, so we'll see it based on this alpha value if that confidence interval holds up to the hypothesis test. Okay, so once we write our hypotheses, we collect our test. We calculate our test statistic. Okay, so T equals. Okay, and that was x bar 1 minus x bar 2 minus mu1 minus mu2. Okay, so x bar 1, okay, that was the 2.97 minus x bar 2, which was 3.25, and then minus mu1 minus mu2. Well, there's a little trick on this one. If mu1 equals mu2, then we could think about what's mu1 minus mu2 equal to. If you subtract mu2 from each side, you get 0. So what's nice with the test statistic is that mu1 minus mu2 generally turns into 0, because you can rewrite mu1 equals mu2 as mu1 minus mu2 equals 0. Okay, so you're just going to end up with x bar 1 minus x bar sub 2. And then divided by that square root of s1 squared over n1 plus s2 squared over n2. Okay, and when you do that arithmetic, again, it's just calculator work. Okay, what I suggest you do is you can do 2.97 minus 3.25 and then press enter, or put it in parentheses, okay, because you have to make sure your order of operations is correct on this. And then divided by, you can enter that whole square root in your calculator all at once. And when you do all that in your calculator, you end up with negative 3.242 for the test statistic for T. Okay, so I suggest that you can pause the video and make sure that you get that number on your calculator, okay, or else you're going to miss it every single time. Okay, so make sure that you get the order of operations correctly. Once you find the test statistic, now remember we need to look at making our decision Okay, so we look at our t-distribution, and we want to know, is that difference, 2.97 minus 3.25, an unusual difference if mu1 really equaled mu2? Okay, so basically, are those two values too far apart from each other based on their distributions in order for that null hypothesis to be a faulty assumption? Okay, so if we locate negative 3.242 on the t-axis, okay, it'll be somewhere over here. And the fact that we're looking at the alternative being mu1 is less than mu2, that means we're looking at the left-hand tail, or the left end tail, for our rejection region for the test statistic. Okay, so negative 3.242. Again, that was our test statistic. And the idea is that too far away from the center of the distribution for our assumption that mu1 equals mu2 to be a faulty assumption? Okay, so we need to know if our alpha value is 0.05, then what t-score, or what critical number for t, had 0.05 to its left when you had 84 degrees of freedom. Okay, because again, the smallest sample size was 85, so n minus 1 degrees of freedom will give us 84 degrees of freedom. So when we go to our t-distribution, 84 degrees of freedom, alpha is 0.05, and we're going to be in one tail because we have mu1 is less than mu2. So we're going to be shading to the left. So if we have 0.05 in our one-sided p, okay, so one-sided p means you're in one tail. Okay, so 0.05, 84 degrees of freedom. Well, again, we skip from 80 to 100 here, so we're going to go to 1.664. Because we're on the left-hand end, it's going to be negative 1.664, which will be between 0 and negative 3.242. So we know that our test statistic is going to be somewhere right here, negative 1.664. Okay, so that value has alpha equals 0.05 to its left. So our test statistic is well beyond that. Okay, so that means that test statistic, or the difference in the sample means, is more extreme than what we would have expected to have happen if the mean for the users really was equal to the mean for the non-users. Okay, so what that tells us is we reject HO. Okay, again, because negative 3.42 is farther out to the left than our critical number for T was. Okay, based on the 84 degrees of freedom and alpha being 0.05. Okay, so our decision is to reject HO, and if we reject HO, that means that we support the alternative, which was the claim. Okay, so there is enough evidence to support the claim that mu1 is less than mu2. Now I ran out of room here, but what that means is, okay, it's going over here. Students who use the social media site have a lower mean GPA than those who don't. Okay, I shortened that up a little bit. Okay, basically saying that it does appear that the students that use the site have a lower mean GPA, the population now. okay, have a lower GPA than those who do not use the site. Okay, again, so you can see the process is the same. The only difference now is when you set up your hypotheses, you're looking at comparing two different means, not that mu1 equals a number, okay, like 3.1. Now we're looking at, does mu1 equal mu2? Okay. Okay, our test statistic is just using a different formula, but the same concept. Once you get the test statistic by substituting your values in, okay, you have to compare that test statistic to our critical number that's based on our alpha value, in this case of 0.05. Okay, so our critical number for t was negative 1.664. And it's probably a good practice to find that value first, the critical t number, before you put the test statistic on the axes. Okay, it's probably good practice to do that. Okay, I did it backwards in this one. Okay, if we look at the next example, okay, a gym is concerned about how to allocate their resources to our customer service. They want to know whether men and women spend the same amount of time at their gym. The times for men and women both follow an approximately normal distribution. Okay, so that's good because we don't care what the sample size is now. The central limit theorem will tell us that if the original populations are approximately normal, then we can use our test statistic or our confidence interval formula and feel fairly good about our results. So the gym manager takes a simple random sample of 25 men and 30 women. Okay, and again, these are independent populations because the men and women are coming from two different populations. You're not going to have men and women in the same sample. So the mean for the men is 47 minutes with a standard deviation of 4.2 minutes, and the mean for the women is 51 minutes with a standard deviation of 6 minutes. So construct a 98% confidence interval for the mean difference in men and for the mean difference in time. Okay, so for the mean difference in time that men and women spend at the gym. So that the mean difference we're looking at, population mean difference, we're looking at mu1 minus mu2. So here you can define the first group to be the men. Okay, so you can say like group 1 is the men and group 2 is the women. Okay, we have 24 degrees of freedom because there were 25 men and 30 women. So those are sample sizes. So 25 is a smaller one, subtract 1 will give us 24. Degrees of freedom. Okay, so doing a 98% confidence interval. Okay, I think you should be able to do this. So for the sake of time on the video, I would say pause the video and see if you can pick out the values and substitute them in. Okay, we're doing a confidence interval, so you're looking at this right here, x bar 1 minus x bar sub 2, plus or minus the t star times that standard deviation here. Okay, or the standard error, I should say. Okay, so plug into that formula. And again, if you want to pause the video, go ahead, but I'm just going to put the values in on here so we can keep on moving. Okay, so when you do your confidence interval, we get a margin of error of 3.44. Okay, and that'll be 3.44 minutes. So we have -4 plus or minus 3.44. That -4 is coming from x bar 1 minus x bar 2. That was the men sample mean minus the women's sample mean. Okay, so it looks like, to start with, it looks like that we have men spending less time than women. And then we're adding and subtracting that margin of error, and we end up with a negative value for the lower and upper bounds of our interval, which, just like the last one, what that's telling us is that we're 98% confident that our interval contains the true value of the population difference in means. Okay, so what it looks like is, because both of those are negative, again, coming from the idea that x bar 1, the men, minus the women's mean, ended up being a negative value, so that means that the men spend less time than women. Okay, it looks like this interval supports that idea, okay, that men spend less time in the gym on average than women. And again, if that was a positive, so if this one was still negative 7.44, and the other bound would just say it was positive 0.56 or positive anything, okay, then 0 would be in that interval, which would indicate that 0 is a realistic possibility for the difference in the population means, mu1 minus mu2. Okay, so what that would tell you is, again, if that was a positive there, if 0's in the interval, then you couldn't say that there was any difference between the time spent in the gym. Okay, if it happened they're both positive, so let's just suppose it was, say, positive 0.56 to positive 7.44, then what it looks like is that men spend more time than women. Okay, so if they're both positives here, and 0's not in the interval, so they're both positive, that would indicate that men are spending more time than women. So if you define these backwards and said that 1 was the women and 2 was the men, that's fine. It's just going to reverse these two numbers. Everything else is going to be the same, but then you'd have positive answers here for each of them, positive 0.56 and positive 7.44, and that would just tell you that the men are spending more time, or I'm sorry, the women are spending more time than the men. Okay, that's just wording this a little bit differently. Same meaning, but just worded a little bit differently. Okay, if we do a hypothesis test to test the claim that men and women spend the same amount of time on the gym on average, and if we use an alpha value of 0.10, so for the hypothesis test, we're going to make our hypotheses. Okay, the same amount of time would be that mu1 equals mu2. Okay, so the mu1 equals mu2. And the same amount of time, well, that's what they're trying to claim, is that mu1 equals mu2. So that would be their claim. Well, the opposite of the same amount of time would be not equal to, or the population mean would not be the same. Okay, so here, calculate our test statistic. Okay, in the end, just a matter of substituting into our formula for the test statistic. And we get a t value of negative 2.898. Okay, so there's our critical number, negative 2.898. Make our decision. Well, if alpha is 0.10 and we have 24 degrees of freedom, okay, so on our diagram, this is a two-tailed test because the not equals to means we're going to be shaded in either direction, okay, meaning that the mean difference could have been negative, or the mean difference could have been positive. Okay, so we're in both ends. The negative 1.711, that is our t, the critical number for t, with alpha being 0.10. So that's 0.10 and 2 tails. Okay, right here. And then with 24 degrees of freedom, that's 1.711. Okay, so that's where that number is coming from. So negative and positive, 1.711. If you split the 0.10 into the 2 tails, that's 0.05 on each end. Okay, so that's your alpha over 2. And our test statistic of negative 2.898 is farther to the left of negative 1.711. So what that tells us is to reject HO. And if we reject HO, you got to be a little careful on this one, because usually our claim is the alternative hypothesis. But because they wanted to test whether the men and women spend the same amount of time, the HO was our claim. So if you reject HO, now you're rejecting the claim that mu1 equals mu2. Okay, so there's enough evidence to reject that they spend the same amount of time. So it appears that men and women will spend different amounts of time on average at this gym. Okay, if we go on to the last few examples now, okay, we're going to take a slightly different twist on these. Okay, so a drug company may claim that a certain drug decreased cholesterol levels by more than 15 units. Okay, to test the claim, we form hypotheses, collect a sample of size n, calculate the test statistic, then we make our decision. Okay, this would be an example of a matched pair design because you need data in the form of a before and after, and then calculate the difference in cholesterol level for each individual. And then that difference will be compared to a value, okay, like 15 in this case. Okay, so that matched pairs design is important to understand. Your data is in the form before and after, so somebody before may have had a cholesterol level of, I don't know the exact numbers of cholesterol, but let's just say the before their level was 160, and then after, okay, so they get some kind of treatment, after it may have been 130. So if they started at 160, you take that same individual and match them up with their after value of 130. So that would be a difference of 30 for that person, okay, 160 minus 130. Okay, so every individual in that sample would have a before and after. Okay, that's why it's called a matched pair, because each individual is going to be a data value before and after. Okay, so HO and HA for that example. Okay, what you would try to be, what you would be looking